The topic that he's speaking on today is building trust in your software supply chain with SLSA. We all know how vital is a software supply chain, but this is how you can actually build trust in your software supply chain with SLSA. Without further delay, I request Mr. Subrahmanyam to take over the stage.
It's great to have you in the 18th edition of Open Source India, and thanks for joining me. In this session, I would like to highlight the importance of building trust in your software supply chains and how you can achieve this using SLSA and Google Cloud. My name is Prashanth, and I lead developer advocacy for Google Cloud in India. In the next 40 minutes, we will look at trying to understand what is a supply chain. Then we will look at some of the attacks on software supply chains, followed by how we can secure these supply chains. We will do a quick demo at this point, after which we will resume with understanding how Google Cloud can help build security into the software supply chains, followed by another demo. Finally, we will end with a recap and we can take some questions. So, some of you might already know what a supply chain is, and even if you're hearing this for the first time, I'm sure you're having the right idea forming in your mind. Let us try to understand what exactly the software supply chain is, though. So the software supply chain, simply put, is a journey of code, configuration files, deployment specs on the path to production. Right? The code, configuration files, and deployment is what we call the artifacts. This journey is analogous to a manufacturing supply chain, which is where the term originally comes from. The car you drive, for instance, is made up of thousands of parts from hundreds of suppliers. Likewise, software products often leverage dependencies from hundreds of third parties and open source libraries. Next, just like how your car parts are shipped and stored in warehouses before they make it into your car, software dependencies are stored in repositories, be it source code repositories or artifact or image repositories. Finally, just like the car which is assembled from parts before it hits the showroom, your dependencies are combined with your code in a CI/CD pipeline and it gets built before the customer gets access to either your products or your service. Looking now specifically at how code is written by a developer and resides in a source code repository, is then combined with dependencies in a build process and is finally deployed as a software or a service to the end user. Modern software delivery patterns have remained rather static since the adoption of continuous delivery pipelines. However, simply implementing continuous delivery pipelines to deploy software does not ensure that the code is verified for authenticity, nor does it provide a guarantee to be safe and secure. Common weakness enumeration (CWE) and common vulnerabilities and exposures (CVEs) are often deployed to environments without knowledge, introducing security risks that could have been avoided using a secure software supply chain methodology. So what are these supply chain attacks and why should we care? Supply chain attacks are definitely not new. Let's take a look at some of the attacks that we have seen in the wild in the past. In 1984, Ken Thompson planted a piece of code in Unix which created a backdoor. This was not a malicious intent, but he did this to prove a point of how one could introduce bad code and compromise a system. The hack was never exploited. Recently in 2017, there was a massive attack called NotPetya. Here, hackers compromised the software system of popular software packages and pushed out a malicious update. This crippled countries all over the world and is regarded as one of the costliest cyber attacks in history. Much closer to today, and what is very well known, are the SolarWinds attack. This was an attack on a single company's software but turned into a major supply chain incident affecting a large number of organizations, including the US government. The hackers planted malicious code in the performance management system, which had privileged access to the ID systems, hence compromising the data, network, and systems of thousands of organizations. Then in 2021, A CVE in a popular software allowed attackers to bypass authentication and impersonate as the admin. The software that you produce, if not secured, could lead to compromising your downstream systems and users. And most recently, hackers modified a bash uploader script to potentially access end user information. They took advantage of the way in which Docker images were built to gain access to Git credentials and thereby exploiting more data and secrets. Therefore, it's super important to keep your code repos clean and build secure deployment pipelines. As we look at these examples which caused widespread damage, every single link in the software supply chain is a potential target and can be breached if not secured. Injecting malicious code to compromising source control, injecting or compromising your dependencies, altering the build pipeline, and even bypassing it to deploy bad software. And finally, compromising the package manager or tricking the end user to using a bad package. And this is what is known as typo squatting. In fact, this threat is so imminent and so impactful that President Biden has recently issued an executive order requiring all federal suppliers and critical utilities conform to forthcoming software supply chain security standards. And we believe that these standards will quickly become the norm across the entire industry. So now is the time to understand and plan how to secure your software supply chain. So let's look at how exactly we can go about doing this. The first step is to understand your supply, or what libraries and frameworks you use to write your code. Open source is heavily used in all software and it can be challenging to determine the risk of open source dependencies. We recently launched Open Source Insights, an interactive visualization site for exploring open source software packages. Open Source Insights is unique in that it provides a transitive dependency graph with continuously updated security advisory, license, and other data across multiple languages in one place. SLSA is another project that we've been working on. SLSA stands for Supply Chain Levels for Software Artifacts. It has been developed in direct response to the known supply chain attacks. Any software can introduce vulnerabilities into a supply chain, with recent high-profile cases proving how costly an attack can be. The steps that make up the SLSA framework aim to empower developers and software consumers to easily and automatically check the integrity of software artifacts. SLSA levels are a way to better understand your current security posture, protect yourself from potential threats, and plan for the future. If you're a software consumer, you can check that the security information for any software in your supply chain is accurate and whether it provides the exact level of security you need. This framework is constantly being improved and is now ready to be tried out and tested. Google has been using an internal version of SLSA since 2013 and requires it for all of the production workloads. So let's look at the SLSA levels. At level 1, we expect that you have a fully scripted build process. The provenance is generated and gives information about the artifact, build process, and dependencies. At level 2, all code should be version controlled. The build service must be hosted and not running on a developer's laptop. The provenance must be authenticated and verifiable. At level 3, the source and build platforms must be audited and certified, so that the provenance is tamper-proof. Finally, at level 4, all code has to go through a 2-person review process, and the build process has to be hermetic and reproducible. This is the framework that we seek to establish. As I mentioned, this is in alpha, and let's take a look at a quick demo to see what SLSA can do for you and how to actually start leveraging it. Now, what I have done is SLSA, the example that is present here can generate a build provenance. So what I've done is I have my own GitHub repository. And in this, what I'm going to do is I'm going to demonstrate how somebody would utilize the SLSA provenance generator within GitHub in order to create a build provenance. In order to do this, I have utilized the actions capability of GitHub. and I have created, and let me go to this, go to the code. Yes, so this is a YAML configuration where I'm generating a build provenance. The first part is typically in a build pipeline, you create a build artifact, right? In this case, I'm keeping it simple. I'm just creating a zip file. Once a zip file is created, I upload this as the artifact. We will then sign this artifact using the provenance generator. In a typical case, what I would do is a user would come in, and I am going to come into the main code, add a file, and I will say new file. Once the developer makes some source code changes, the developer submits this. In a typical process, you want to ensure there's a 2% review process, and hence I'm not going to commit directly to the main branch, but I am going to create a pull request to merge this file in. Once this is done, let me open up the actions in a separate tab. You see nothing is happening here. Typically at this point is where once I create the pull request, the maintainer, or let's say some of the owners on the project, will be looking at this file. We'll be trying to understand if there are any bugs, if there's any malicious intent, and if the file is generally acceptable to be submitted. Once the commit is ready, the pull request can be accepted. So let's accept the pull request. All right, now that this file is pulled into my repository, we will see that the new workflow has triggered, and this workflow is executed as soon as a push is made to the main branch. The two steps as part of this workflow is first to build the artifact itself, which, as I mentioned, in this case is just a simple zip file. Typically this is where you would compile your code, you would either create an image, you would run your make files and so on. But in this case, I'm just going to create a simple zip file. Subsequently, I will be signing the zip file and will be uploading this as an artifact. Now, this provenance and this artifact can be traced back to ensure that it comes from a trusted source, and we will be able to trace back the history of how it has been built. Let's go into the generate provenance build step. Yes, this is complete. Going into the job summary, we will see that the artifacts that have been produced during runtime are present here. Let's download this artifact. Right. And I am going to take this artifact over. All right. Sorry, and yep. All right, so we see that the zip file which was built is present here, as well as a build provenance. Now this zip file is what the artifact is. This is what could be malicious, and hence the build provenance is important, which will let us know whether the file is a good file or not. This uses the in toto attestation specification, and you will see here a lot of digests and a lot of information about how this build was generated. You can see the predicate, you can see where the build was made, and if I take this run the build invocation ID, this is the traceability. So if I take this, go back into my browser and paste this, this should take you exactly to the build that was run which generated this artifact. And this is your traceability, right? This is how you check that you check your provenance to determine the source of the piece of code. The second thing is the digest, right? So we have the SHA-256 digest, and I'm going to copy this. Let us check that the build file is valid. So I'm going to take the build.zip, and we will check that the latest digest that I copied from here matches what is there on the build file, right? That matches. So which means that this artifact is now safe for me to use and does not have any malicious intent, or nobody interjected into the build pipeline. All right. So that was the demo for SLSA. Now, what is the approach that we are taking with SLSA? What did we look at right now? First thing is there are multiple levels. So we encourage you to take a progressive approach to security with the level idea. Build your system so that you automatically generate provenance, integrate the provenance generation into your review process. Finally, script your builds and use a hosted build service. These are the recommendations that we are coming in from SLSA. And again, SLSA is an alpha framework. We would like to encourage your participation so that we can help build a better framework for the industry to use. For you as an enterprise, this security does not have to come at the expense of developer velocity. And this is precisely why at Google Cloud, we are providing a set of managed services for the end-to-end process of developing and deploying software, making security ambient by quietly taking care of this in the background while allowing your developers to go fast securely. Google has built security into every layer of our infrastructure and our internal software supply chain. It starts from the physical security of our data centers and hardware to software and data protections to securing internet communication and support operations. This is why Google Cloud's managed services can help your overall security posture. Aside from using managed services, it's equally important to secure the software you create from supply chain threats. Securing your software requires establishing, verifying, and maintaining a chain of trust to establish the provenance or origin trail of your code via attestations, which are generated and checked throughout the software development and deployment process. At each stage of the software supply chain, we provide you with solutions to help you apply security while maintaining release velocity. With Google Cloud, you can create a build pipeline using Cloud Build to sign the build and create an attestation that shows when the build was made, what triggered the build, and whether there were any critical vulnerabilities. Notably, Cloud Build today helps with achieving a SLSA level 1. Cloud Build captures the source of the build configuration, which can then be used to validate that the build was scripted. As you know, scripted builds are more secure than manual builds, and this is a SLSA 1 requirement. Also as required, this provenance and other attestations can be looked up using the container image digest, which is a unique signature for an image. Google Cloud Build is a fully managed cloud service. This means in addition to developer agility, this service gives you a lockdown environment for securing builds. This greatly reduces the risk of compromised build integrity or a compromised build system. So once the build is complete, it goes and gets stored in the Google Cloud's artifact repository, where it is automatically scanned for vulnerabilities. This generates additional metadata, including an attestation for whether an artifact's vulnerability results meet certain security thresholds. This information is stored by our analysis service, which structures and organizes an artifact's metadata, making it readily accessible to services like binary authorization. Having built, stored, and scanned the images securely, we are now ready to deploy. At this point, the attestations are captured along the supply chain. The attestations which were captured along the supply chain are verified for authenticity by binary authorization. In enforcement mode, the image is deployed only when the attestations meet your organization's policy. In audit mode, the policy violations are logged and they trigger alerts. Binary authorization ensures only properly reviewed and authorized code gets deployed. That was a lot of talk about binary authorization, but let's have a look at it in practice. Let's take a look at a demo now. All right, so let's take a look at the demo. On one tab, I have my Cloud Shell opened, and the other, I have my project. The way my project is set up is that I have 3 Kubernetes clusters created: dev, QA, and prod. And in order to use binary authorization, I need to ensure that binary authorization is enabled for each of these clusters. Doing this change will cause the cluster to restart, and hence I have already enabled it right now for the purpose of this demo. Now, while we get started, I have a simple image which is using the Nginx image, and I'm building a custom landing page. So this is there as a Docker file. I am a developer. I'm working on my piece of code, and let's assume that this is the source code that I'm working on. The first thing that I'm going to do is I'm going to build my image. All right, so the Docker image is getting built, and as soon as this is built, we will run the Docker image. All right, and let's take a look at what's running. Great. So this is the S3C demo and a simple Nginx server with my custom page. The Docker image is fine. As a developer, I'm working on my local machine and I'm satisfied with what I've built. The next thing that I do as a developer is to deploy this into a Kubernetes cluster and take a look if the application is running there. So the way I do that is I first upload this into the container registry. So what I've done is I have configured Cloud Build. As we have mentioned before, your build has to be scripted. This way you can ensure that the build script is pushed into your source code repository. Any changes to it are audited and verified by 2 persons. Let me check if there are changes. All right, there are changes. Git add all is typically not a good idea, but I'm going to do this right now. Of course, I need to push. All right, now that my changes are pushed, Cloud Build should pick up the changes and trigger a new build. Right, there you have it. A new build is being triggered. Once the build is complete, I will be able to go and deploy this into the development cluster. All right, the build is now complete. Oh, sorry, that wasn't to be done. And what I will do now is I will deploy the latest Nginx image, and let me just show you what is there. So this is going to pick up the latest image, Nginx image from the container repository, and use the image name or the image path and the digest in order to deploy it. So we're using kubectl create -f deploy nginx YAML, and that's what's going to happen now. This is the image that is being used. This is the latest image that was built just now, and it has been deployed. Looking at this, we have the container being created, and in another minute the container should be deployed and running. All right, so the container is deployed and it's running fine now. This is the development environment, right? Typically you have lesser security in here. As you build images, you have tested it locally. Now you want to test this in the environment to ensure that it is working fine. However, let's now start introducing some of the authorizations that we want to do. So I will go into binary authorization. In binary authorization, there are 2 parts. The first part is a policy, where the policy you define what is allowed and what is not allowed. And the second thing are attesters, where you sign certain images or based on certain conditions. For example, if an image passes the QA, then you would probably attest it, right? So let us implement some of these policies here. The first thing, as you see here in the policy, is that it is set to allow all images. This is something that we want to restrict. So what we will do here by default, the global policy is we will disallow all images. We will allow some of the Google provided system images because this is used for maintenance reasons, for the cluster to upgrade and so on. And we will create cluster specific policies. So the first thing that I'm going to do here is, which is not going to change anything that has happened right now, is I am going to use a dev cluster and allow all images. So globally I have disallowed all images, which means if I run that kubectl command again, it's not going to work. So I will allow all images for the development cluster. Save the policy so that it saves, so that it reflects. Now the changes that we have here, we are trying to ensure that there is a build provenance, right? What we've done is Cloud Build has definitely run this. However, what is a guarantee that the image that we are going to be deploying was actually built by Cloud Build? And what we will do now is in the QA cluster, we will ensure that only the images that have been built by the Cloud Build and signed by Cloud Build is allowed to be deployed. In order to do that, I will create an attester. I will call this build attester, and I will use, we will automatically generate an analysis node, and we will use a key from the Cloud KMS. I'm just going to get the key that I have already created. So I've created a few keys in the Cloud KMS, and we will use the build signer key that has been created. So this is an asymmetric key that is used for signing. Okay, so that's a build attester created. And now we will add a policy for the QA cluster. To allow images, only those images that have been signed by the build attester. All right, so now images can only be deployed to the QA cluster if they have been signed by the build attester. Let us now try this. I will now switch my context to the QA cluster. All right, my kubectl will now point to the QA cluster, and I'm going to do the same thing. I'm going to go deploy the file that we previously deployed into the development cluster. Okay, this is still going to get the latest image and is going to be deploying it. What we see here is that this has been denied by the always deny admission rule. Right, so binary, it has been denied by binary authorization. Now, in order to allow this to be deployed, we need so this in fact is the always the rule that's here is the always deny admission rule. The always deny admission rule is the overall rule which is disallow all images. I hadn't saved the policy. Let us go and deploy this again now. All right, now this makes a lot more sense. There were no attestations found, and it has been denied by binary authorization, and the rule that has denied it is expecting a signature by the build attester. Right, this is exactly what we have just now configured. So what we will do now is we will modify the Cloud Build configuration so that it also generates a it also attests the image as it's being built. So I have a sample configuration here, and essentially this creates an attestation after it pushes this to the container repository. It uses an image to generate the attestation, and we are also passing the name of the attester and the key that has to be used in order to sign it. So I will replace the Cloud Build YAML file that we have with this, checking that changes have been done, and sign while sign the build. All right, and pushing this. If we go now into the build, we will see that a new build is being generated. All right, so now this is a new build. If you go into its details, we will see that there is an additional step, which is a create attestation. Now, while this is happening, let me also show you that all of these capabilities of signing, building, who gets to use the signature, who gets to use the key, all of this can be locked down. In this case, I have an IAM rule applied. All right. Now, if I go to IAM, we can see that the cloud build service account is the only one that has been allowed to use the keys in order to sign and verify, and it is the one that is also has the permissions to view attestations, the container analysis roles to create a note, an attestation note, which then gets attached to the image, which is essentially the signature, right? The digest has been signed. So this way you're also locking down who can access these things. It's not that the feature is enabled and anybody and everybody can go and sign this, but you're also locking down which service account and which process can actually go and pick up these keys and do the signature. Now that it has been built, and I believe we are pointing to the QA cluster, I will go and deploy this image now. And previously we saw that this was denied by the policy. Now we see that the image is being deployed. And let's again check this. Yes, so here the container is creating right now. Previously we were connected to the dev cluster and the container was already running there. Whereas here the container is being created in the QA cluster and will start running soon. Yes, there it is. So this is great, right? We have seen how the attestation can be used in order to secure that only trusted builds can be deployed in certain environments. Of course, the same thing is what we will need on the production cluster as well. So I'm going to go and set that. In addition, what I also want to do is I want to ensure that only images that have been scanned for vulnerabilities can be deployed to production. So to do that, first I will create another attester. Let's create a vulnerability attester. Again, we will automatically generate a container analysis node here, and we will import this from the KMS. And again, I'm going to go pick up the key resource ID that I have already created. So I've already created a key for this in KMS. Done, create. Great. So now I have a different attester which uses a different private key, and I can have this as another signing step. All right. What I will do now is I will use the open source Critis capability in order to sign the image that I have created. So previously Cloud Build, when it built the image, it signed it because it was the one that is building the image. Now it is going to call the vulnerability scanner. It's going to scan the image for vulnerabilities, and if the image does not have any vulnerabilities, the scanner is going to attest the image using the provided private key. All right, so going back into the policy, and we will set this up for the prod cluster. The attesters that we want, firstly, we definitely do want the build attester, and then we need the vulnerability attester. All right, so images can only be deployed to the prod cluster if they have both these attesters, if they have the signatures from each of these attesters. Saving this. Great. So now let's go here, and I will have to switch to the production cluster. Yeah, essentially what I'm doing here is I'm using G Cloud container to get the gcloud to get the container credentials so that I associate it with kubectl. All right, now let's go and deploy the image that was last created. And this image is the one that has only the build attestation, not the vulnerability attestation. If everything is in place, yes. So we are expecting a signature from the vulnerability attester, and which is not present in this image, hence it doesn't get deployed. So now I have the configuration for the vulnerability attestation. So if you look here, this is the Critis signer image that is being used, and Critis again part of the Graphias project. So all these are the open source contributions that Google has contributed to as well. And Critis signer is going to scan for vulnerabilities. It will scan according to a policy. In the policy, you can allow list certain CVEs. Maybe you think they are not important for you, or maybe you think that you have a plan to fix it. No CVE is not important. And the other thing is you can set the maximum fixable severity and the maximum unfixable severities. So unfixable I've set it at medium right now, and the fixable I've set it at high right now. Right, so this policy is going to be used in order to scan for vulnerabilities, and I should update my cloud build YAML and push these changes in using the single add and commit command for brevity, and scan images. All right, git push. Cloud build should pick this up now. Right, so while the new image is being built, yep, I could go and show you the KMS in the meantime. So if we go into security and KMS, you will see that I have already created a keyring, and in the keyring I have created 3 key pairs. Right, so for example, this was a build signer, and this is the key that has been created. So it's an asymmetric signing key, and this is where you would get the resource name, which is what I had copied over and which I was using while creating the attesters. Right, so this way even your keys are managed, and as we saw while creating the attesters, if you did not want to use the keys managed by KMS, you could also supply your own OpenPGP keys that you are managing elsewhere. Right, so even that is an option. And we see here that the image is being scanned for vulnerabilities based on the policies that we have set. All right, seems to be completing. It's found vulnerabilities. However, it hasn't found vulnerabilities that go against the policy that we have created, which is why it did go ahead and sign this. The one on top is the latest build with the vulnerability attestation. The one before doesn't have the vulnerability attestations, and let us try to deploy that. So I am going to, oops, that is not what I wanted. I wanted to go into the container registry, go to Nginx, and get the full image name of the 1-. You see here that these are all also the vulnerabilities. So this is the continuous vulnerability scanning that is happening in the container registry, the images that have been uploaded to Google Cloud. All right, so I picked up the full image name and go to Cloud Shell. Let us try to deploy this. Right, so this has been declined because of the vulnerability attester. However, I do want to check that nothing got deployed. Yeah. All right, and If I get the latest image, that should have a valid attestation for vulnerabilities. And do the deployment now, and the pod was created. But of course, it's going to be there. All right, so that brings me to the end of the demo on binary authorization. Of course, there's a lot more that you can do here. Awesome. So what did we see here? First thing, we saw that we could script builds using Cloud Build. We were able to generate attestations for both build and vulnerability scans. So all the attestations were generated. You could have different environments and each of them could have different security policies. And you could ensure that the production environment is highly locked down with continuous vulnerability scanning enabled as well. Finally, we can leverage IAM to close down access to any of these sensitive artifacts, right? For example, the PGP keys or the security keys. In summary, what we did is we took a look at the Google tools that you could use to authenticate and authorize deployments. As you see, when we use Google Cloud to practice these security principles, you can quickly establish and maintain trust, greatly improving your security throughout your software delivery pipeline. All of this is in line with your processes without sacrificing the need for speed or quality. To recap, some of the security practices that we would like to encourage you to exhibit is 1. Secure every link of your software supply chains. 2. Automatically generate provenance and attestations. The key here is automatic. You don't want to do this manually. You want to verify and continuously maintain trust on the artifacts that you are generating and that you're distributing. Bring in your security practices closer to the development phase, as we saw by introducing some of these policies in the Cloud Build. As we are building, as we are deploying to dev environments, you could get the inputs already there in terms of the scanning and the attestations, right? So bring in these practices closer to the development phase, do your vulnerability scanning upfront than waiting for it to go into production. Finally, adopt framework like SLSA.dev. This is a cross-industry collaboration that we are doing in order to get this framework in because of how important this whole idea of securing your supply chains are. So please go ahead and adopt frameworks like SLSA.dev, and most importantly, do get involved in this and share your feedback as well so that we can make this framework better for everybody. All right, with that, we can take any questions, and if we do run out of time or if there is something that you want to ask me later on, as I said, my name is Prashanth. I am available on Twitter at @ksprashu. Please reach out to me if you have any questions and I'll be happy to help you there. All right, with that, thank you for your time and I'll take any questions right now.
Can you share some security protocol which can be used to authenticate from the customer point of view in a device?
Yeah, no, typically there are a lot of such patterns that you could use. And one of the most popular, of course, is OAuth and OpenID Connect. OpenID Connect is something that you would use to identify who the person is, right, for authentication. We have a lot of OpenID providers like Google, like Facebook, Twitter as well. And these logins can be used. Apple is very popular now as well. And of course, OAuth then becomes very important because you want to ensure that your application takes permission from the user, or the end user gives permissions for the applications to access their credentials and do something on their behalf. So yes, I would definitely suggest people to read up on OpenID Connect, on OpenID, as well as OAuth for all the client implementations or app implementations that you do.
Perfect. Thank you, Prashanth. That was a wonderful, wonderful session. Anything you would like to share before parting ways for today?
Oh, no, definitely open source is great. It gives you a lot of agility, a lot of leverage while you're building a product, helps you be really agile. But at the same time, as I mentioned in the session, it's important to be safe while doing it and ensure that your end users are safe. So a lot of such projects that we are running, Salsa, Graphia, Scritters, please do come and please do contribute, and then feel free to connect to me and we can collaborate and work on this together. Thank you.
Thank you, Prashanth. That was a wonderful session.